Good morning, students. Today we are going to discuss about Poisson's ratio and elastic potential energy in a stretched wire. First, we are going to discuss about Poisson's ratio. See here, in the case of Young's modulus experiment, in case of Young's modulus experiment like this, when you apply force on the stretched wire, the length will be changing. Consider the elongation. Elongation is equal to delta L and original length is nothing but L. After application of deforming force, the elongation is delta L and original length is nothing but L. So here longitudinal strain is given by, longitudinal is nothing but along the length. Elongation, strain is taking place along the length. So here longitudinal strain is given by delta L by L. Now see, by observing carefully, when the length increases, the area of the wire decreases. So when deforming forces are there, when deforming forces are there, by observations, when length increases, there is a reduction in area of the wire, that is reduction in diameter of the wire. Okay, this reduction taking place perpendicular to applied force. So we call this strain as lateral strain. Lateral strain is nothing but, here lateral strain is change in diameter, that is reduction in diameter divided by original diameter. So lateral strain equal to delta D divided by D. Here lateral strain is proportional to longitudinal strain. If longitudinal strain is more, the lateral strain also will be more. So by removing proportionality symbol, we will get some constant. So that is lateral strain is equal to some constant sigma into longitudinal strain. Therefore, here the constant sigma is equal to lateral strain divided by longitudinal strain. Here the ratio of lateral strain to longitudinal strain is called Poisson's ratio. We call this sigma as Poisson's ratio. How we will define Poisson's ratio here? Poisson's ratio is equal to the ratio of lateral strain to longitudinal strain. So here Poisson's ratio sigma has no units, no dimensional formula. No units and no dimensional formula. No dimensions. Okay, this is all about Poisson's ratio. Now we are going to discuss about elastic potential energy. Elastic potential energy in a stretched wire. So when a wire is put under some deforming force, there is a increase in length when wire is put under tensile stress. Tensile is nothing but, in the case of tensile, the length of the wire will be increased. Under tensile stress, there is a increase in length. Increase in length. Let us consider original length is capital L. Original length is equal to capital L, and increase in length is equal to delta L, that is equal, let us consider small l, and see, by application of force, more force, the further increase, consider the further increase in length, is equal to delta small l. Okay, so here, because of this deforming force, work done is taking place. Because of the application of force, there is a change in length. A force into length is nothing but, force into displacement is nothing but work done. That work done can be stored as the potential energy in a stretched wire. So here the work done by force is given by dW equal to FdL. So here we know that from Young's modulus formula, Young's modulus equal to F into L by A delta L. Okay, so Young's modulus, here I am taking force F equal to YA delta L divided by L. So here F is equal to YA delta L, we consider it as increase in length as small l divided by capital L. So this is the formula for force. So I am substituting dW here. For total work done, we need to integrate it. So complete work done equal to integral dW, that is equal to integral FdL. So here work done equal to integral, what is force here? YA small l divided by capital L into dl. Okay, so work done is equal to, here I am taking Young's modulus is constant for a given material. I am taking it as common. Area is also constant. I am taking it as common. Length is also constant. Here length is changing from 0 to L into L. The remaining thing is L dl. So we know integral x dx is nothing but x to the power of 1 dx is nothing but x to the power of 1 plus 1 by 1 plus 1. So here work done is equal to YA by L into L square by 2. So this is the work done in stretched wire. This can be stored as the potential energy in a stretched wire. So Y. So here I am taking 1 by 2 Y A by L into L square is there. Okay, I am rewriting it as half into Y into, here I am writing it as L square divided by capital L. The remaining thing is area. So here I am doing L divided by L. So work done is equal to, here L divided by L is nothing but we will get 1 again. So work done equal to half Y into L is nothing but L square. Capital L square by small l square into the remaining thing is A into L. Area into length is nothing but volume. So work done is equal to half into Y into small l by capital L whole square into A into L is nothing but volume. Okay, so here the work done is given by half into Young's modulus. Young's y is nothing but Young's modulus into here uh, L by L. Small l is nothing but what? Small l is increase in length. Delta L by L is nothing but strain. Small l by L is nothing but strain. So strain whole square into here. L by L is nothing but strain into volume. Into volume. So work done in this case is given by work done equal to half into Young's modulus is nothing but stress divided by strain. Stress divided by strain into strain square into volume. So here strain and one strain get cancelled. So work done is equal to half into stress into strain into volume. Energy, work done is nothing but energy. Energy per unit volume is equal to half into stress into strain. Here work done per unit volume is also called as energy per unit volume is equal to half into stress into strain. Okay. Here the leftover problems in this chapter are 6, 10 and 15. Now we are going to solve the remaining problems. Those are 6, 10 and 15. So here the sixth problem is talking about here the sixth problem is a brass wire of cross-sectional area. A brass wire of cross-sectional area A is equal to 2 millimeter square, that is 2 into 1 millimeter is nothing but 10 to the power of minus 3 meters whole square, that is 2 into 10 to the power of minus 6 meters square. So area is given. A brass wire of cross-sectional area is suspended from a rigid support and a body of volume 100 centimeter cube. So here the situation is like this. The brass wire is suspended from a rigid support and another end of the brass wire is attached to a body of volume. Volume of this body is 100 centimeter cube. So volume is equal to 100 centimeter cube, that is 100 into 1 centimeter is nothing but 10 power minus 2 meters whole cube, that is equal to 100 into 10 to the power of minus 6 meter cube. This is the volume. Now it attached to other end. If the decrease in length of the wire is, decrease in length is nothing but delta L equal to how much? 0.11 mm, that is 0.11 into 10 to the power of minus 3 meters. Now when the body is completely immersed in water, when this body is completely immersed in water, there is a buoyancy force, upward buoyancy force. Because of that upward buoyancy force, there is a decrease in length. Here the buoyancy force exerted by fluid on the object is called buoyancy force. So that buoyancy force equal to weight of the displaced fluid. So here consider this is buoyancy force. As this buoyancy force is acting upwards, so there is a decrease in length of the wire. So here buoyancy force is equal to weight of the displaced fluid. Weight of the displaced fluid. We will discuss in detail about the buoyancy force in next chapter. So weight of the displaced fluid. Weight is nothing but mass into acceleration due to gravity. Mass is nothing but density into volume into g. So here The deforming force is nothing but buoyancy force, and the buoyancy force formula is density into volume into acceleration due to gravity here. So here he asked to find out, the question is find the natural length of the wire. What is L here? What is L? So here we know Young's modulus Y is equal to F into L by A delta L. Here he asked to find out length. So I am rearranging the terms as the length L is equal to Y A delta L, Y A delta L divided by F. So now the length, original length L equal to Y is given, Y is equal to 0.99 into 10 to the power of 11, 0.99 into 10 to the power of 11, am I right? 91, sorry, 0.91 into 10 to the power of 11, this is Y value into area. Here the area value is how much? 2 into 10 to the power of minus 6 into delta L. Here the delta L value is how much? The delta L is equal to 0.11 into 10 to the power of minus 3 divided by F. Here the force F is nothing but density into volume into G. Here the density value is given by density of water equal to 10 to the power of 3, that is 1000 kg per meter cube, into force is nothing but density into volume into acceleration due to gravity. Density value I have written. Volume is equal to, how much the volume is given as 100 into 10 to the power of minus 6 into G value is 9.81. By solving this, you will get the answer for L. Okay, this is all about solution for problem number 6. Now I am going to discuss about next problem, problem number 15. The problem number 15 is a steel wire of length L equal to 20 centimeters is stretched to increase its length by 0.2 centimeters.